This is How to Math with Dr. Ian Lundholm. In today's episode, sequences. All right, you may notice that I have a sequence here called the Fibonacci sequence, and it's made up of the terms 1, 1, 2, 3, 5, 8, 13, so on and so forth. This sequence is famous because of its relationship to the golden ratio, phi, and often Fibonacci numbers are found in nature, just like the shell that you see here on the right. The first thing that we need to do in today's lesson is to define sequences and to understand the notation associated with sequences. Sequences are just long lists of numbers. Very long, in fact, because an infinite sequence is a function whose domain is the set of natural numbers. Now, in calculus, we normally work with functions whose domain is the real numbers, meaning that we're allowed to use fractions and irrational numbers for our x values. But today, we're going to focus on function whose domain is made up of natural numbers. Let's see if I can highlight that for you. Natural numbers. And natural numbers are just the whole numbers that we're used to counting with. Also notice that we use notation like a sub 1 or a sub 2 to refer to the first or second term in a sequence, rather than using the traditional function notation with parentheses. That's really just a convention in our book, but that's what we're going to stick with for this lesson. Let's look at example 1. In part A, we have a sequence 1, 4, 9, 16, and on. These look like perfect squares. That's why you see this formula, a sub n equals n squared, right here. And this formula is what we call an explicit formula. Because you're able to substitute in your term number. So say if you're looking for the 10th number in this sequence, you're able to plug in the number 10 in for n. You take 10 squared, and then you get the value for the 10th term in your sequence, which would be 100. So an explicit formula allows you to jump to any n value that you want and immediately get the value of the nth term. In part B, we have a sequence here that oscillates between 1 and -1. And you can see that we have the formula b sub n equals -1 to the n plus 1 power. This is an interesting example to look at because it illustrates the differences between sequences and sets. Because in a sequence, all of the infinitely many -1s and 1s that are there in their specific order are important. Whereas if we were just listing the elements in a set without any repeats, we just get the set -1 and 1, and that's a very different object than an infinite sequence that we're looking at. In part C, we introduce some new notation. You can see that we have curly braces with an n equals 1 and an infinity there. That tells us that we're counting from n starting at 1 and moving on to infinity like we normally do in calculus. And this function's actually pretty special. It's made up of a rational expression where we've got n over n plus 1, and those, for different values of n, give us the familiar fractions like 1/2, 2/3, 3/4. When n is 4, we get 4 over 5, and so on. yeah, that has some cool properties that we'll talk about soon. And finally, part D here, you can see that we're using the notation curly braces n from n equals 5 to infinity. And here we have cleverly re-indexed our sequence so that it's in a simpler form. It would have been more straightforward to write this sequence initially starting at n equals 1 and going to infinity as n plus 4, but this one up here is just nicer to look at if we start off at n equals 5. And really that's just for aesthetic purposes. It's not that you have to simplify the notation all the time, but it's just something that you can do if you want to. You don't always have to strictly start at 1 for your n values. Now I would like to get back to Fibonacci. So we're looking at this sequence again. And the question that I'd like to ask is, can we look at this sequence and come up with a formula for the terms in this sequence? I wouldn't expect you to be able to do that right off the bat if, you're just looking at the numbers. But if you have any background, any knowledge of how the Fibonacci sequence is actually calculated, it's made by you get the next number by adding the two previous terms. So for instance, 2 is equal to 1 plus 1. 3 is equal to 1 plus 2. 5 is equal to 2 plus 3. And if I wanted to calculate the next term after 13, what I would do is just take 8 and 13 and add them together to get 21. So 21 would be the next term in the sequence if we wanted to do that. And this relationship actually gives us some way to come up with a kind of formula for this. In mathematical notation, we could say that the nth term, or actually I'm going to use f because this is Fibonacci. F sub n, the nth term in our sequence, is the sum of the n minus 1th term, so the previous term, and the term that precedes this one, f sub n minus 2. So this recursive formula, plus, saying maybe the seed values are of the first term is 1, and the second term is also 1. This provides a recursive definition for the Fibonacci sequence. Let's go with blue here. This is a recursive definition. And it's called recursive because we are defining the nth term in the Fibonacci sequence based on previous terms. Note that in this one, unlike the sequence of perfect squares that we looked at before, if I wanted to throw in the number, n equals 10 and get a sub 10 equals 10 squared, which is 100, that was no big deal. To jump down the line, that's no big deal. But if I wanted to calculate the 10th Fibonacci number down here, let's say f sub 10, then I would need to know the 9th Fibonacci number and the 8th Fibonacci number, and I'm not even sure that we've gotten there yet. We've got 1, 2, 3, 4, 5, 6, 7, 8. So in order to calculate the 10th Fibonacci number, we know that this one's 21, just from all the work that we've done so far, but we'd actually have to do a little bit more work to calculate the 9th Fibonacci number in order to get the 10th Fibonacci number. So a recursive definition is really nice if you just want to know the next number, But this would be even worse if I wanted to know the 100th Fibonacci number, because I would literally need to go and figure out the 99th, the 98th, the 97th, and so on. There's no skipping ahead when you have a recursive definition. There is an explicit formula for the Fibonacci sequence, and it's actually based on the golden ratio phi and phi's little brother, psi, I think is what it's called. Phi is the golden ratio, and it's actually 1 plus the square root of 5 over 2. And I'm going to look this up real quick because I want to make sure I get it right. Yeah, let's bring this down again too. This is something that we actually compute in Math 307 linear algebra, so you guys should look forward to that soon. We actually compute this explicit formula, but the explicit formula would go like f sub n equals phi to the nth power minus, well, really psi is 1 minus phi to the nth power all over the square root of 5. So it's this weird expression built from irrational numbers and taking powers of irrational numbers and then dividing that by an irrational number, the square root of 5, that actually gives you integers that come out of this. This actually gives you the nth Fibonacci number. So if I wanted to calculate the 100th Fibonacci number here, I could just put in 100 for every n that I see and take those powers, and it would actually work. But yeah, that the way to calculate that, at least in a linear algebra sense, is you convert the second order differential equation into a matrix equation, and you look at eigenvalues and eigenvectors, and it ends up being really cool. But that's something that we'll do later. Really, for this example, I just wanted to hammer home the point that recursive definitions for a sequence, recursive definition is different than an explicit definition. And an explicit definition is much better for getting the nth term when n is large. Okay, now we can take a look at this next sequence, and I would like to kind of think about what would be a recursive formula for this sequence, what would be an explicit formula for this sequence, and try to get those down before we move on. In order to figure those out, I think we need to look at what patterns that we see here. We've got 2, 4, 8, 16, 32. One pattern is that those are all powers of 2. And so actually coming up with a formula for the nth term is kind of as simple as saying 2 to the n, isn't it? Because the first term is 2, the second term is 4, which is 2 squared. This would be an explicit formula based on the pattern that we see. All of those numbers are just powers of 2. For the recursive formula, we would need to pay attention to the relationship between successive terms. And so we'd need to be thinking about, like, how is a sub n related to a sub n minus 1, or the previous term? And it looks to me like, every time that you move to the next term, you multiply by 2. So this is what a recursive definition would look like. Recursive. And that's kind of as simple as you get there. And oftentimes in a recursive definition, we'd kind of say that our first term was 2 just so that we had somewhere to start. All right, the next major thing that we need to talk about is what does it mean for a sequence to converge or diverge? And here are the first 4 sequences that we looked at in example 1. We have the perfect squares here for a sub n. Those don't look like they're settling down anytime soon. The perfect squares just keep getting bigger and bigger as n goes on. And so that's an example of a divergent sequence. Here, on the next one, b sub n, it kind of looks like we're oscillating between 1 and -1, 1 and -1, and so on. This is also an example of a divergent sequence because it never settles down closing in onto one specific number. It's a lot like the kind of oscillating discontinuities that we talked about in Calculus 1. For part C here, we have our friendly sequence n over n plus 1, and this is our first example of a convergent sequence because as n goes on, the sequence values get closer and closer to the limiting value of 1. So that's an example of a convergent sequence, and then real quick, d is just a linear function, and that's not settling down anytime soon. So this one would also be divergent. Yeah, formally, here we can look at the definition of a limit of a sequence and determining whether it's convergent or divergent. Let's go ahead and read this. A given sequence, a sub n, has the limit L if for every number epsilon greater than 0, there is a natural number n such that a sub n minus L is less than epsilon for all n greater than big N. We write the limit as n approaches infinity of a sub n equals L, or a sub n approaches L as n approaches infinity, and say that a n converges to L or it's convergent, and if no such limit exists, then a sub n diverges. Woof. Do notice that this definition looks a lot like the epsilon delta definition of a limit that we looked at in Calculus 1. So it's not completely foreign. But here, epsilon, this number, epsilon, acts as an error bound on the limiting value L. Meaning that if someone were to give me an epsilon value, let's say epsilon equals 1/10, I should be able to go to a convergent sequence like sequence C up here, and say that for every term past some big N value, big N, and maybe big N is, I don't know, out here, big N, I should always be able to be within 1/10 of our actual limiting value 1. So if I stretch out and go out to some big value N out here, I should always be within 1/10. So let's say on the upper bound, we've got 1.1. This thing is not behaving right now. There we go. 1.1 and 0.9 as our error bounds here. But yeah, what we're saying is as n goes on, we're always going to be within that error bound as long as we pick our big N to be a big enough number. And so I'm pretty confident that, if we chose N, I don't know, big N in this case looks to be about, 22. If we were looking at the two fractions, 22 over 23 and 23 over 24, I would say it's very likely that the difference between those two fractions is less than 1/10, and it's actually, both of those fractions are within 1/10 of the limiting value 1. So this big N would work for this specific choice of epsilon equals 1/10. In general, this gets more complicated if we actually want to apply this definition. We need to come up with a relationship between epsilon and big N so that it will work for any value of epsilon that we would ever choose. So let's take a look here and see if we can make a little bit more sense of this definition by looking at a specific example. Here we go. We've got two new sequences. For part A, we have that oscillating sequence again that's going to keep changing between 1 and -1. How could we prove that this thing either converges or diverges? Well, we have a hunch that this diverges, right? Because it keeps oscillating. Let's make up an epsilon value and show that there is no big N that we can choose that would satisfy this epsilon value. So let's just say epsilon equals 1/4 for funsies. If we're looking at this sequence that oscillates between 1 and -1, that was kind of horrible. These should be staggered a little bit better. Boom, boom. We want it to be a function of the real number or the natural numbers. And we were trying to put error bounds on either the limiting value where we would be at 1 or the limiting value down here at -1. Neither one of those error bounds where we've got, -7.5 and -1.25 down here, or 1.25 up here and 0.75 right there. If we choose to have our error bounds on the top like this, then we don't include any of those bottom sequence portions or those sequence terms. And likewise, if we chose the bottom, none of the points in the top would be included. And so by choosing our error bound to be 1/4, we are necessarily restricting ourselves to only half of this sequence. And if we wanted to change this thing so that it was made up of two different subsequences, then we could actually say that one of the subsequences has a limiting value at L equals 1, and the other one would have a limiting value at L equals -1. But as an entire sequence, this thing converges because for epsilon equals 1/4, there's no way that we can capture all of the points in that sequence after some term big N. For part B, it's a little bit more tricky because for part B, we're actually going to try to prove that this thing does converge to the limiting value of 1. Okay, and so for that, we would be using our definition. The definition up there looks like you take the difference between the sequence terms and your limiting value, and you want that to be less than epsilon for all little n greater than some big N. So in this case, we're working with n over n plus 1, and we're taking its difference with the number 1, and we want that to be less than some epsilon. Now, a nice thing here is that when we take the difference between 1 and n over n plus 1, that difference is actually, inside the absolute values, it would be negative. If we make the minus 1 into a common denominator, then we'd have n minus n plus 1 on the top. So we actually end up getting negative 1 over n plus 1 here in terms of, subtracting there. And so this kind of tells us a relationship between how far the nth term is going to be away from the limiting value 1. It's going to be 1 over n plus 1 away. And so if we choose that, n is bigger than 1 over epsilon, that means that, 1 over n is, less than epsilon. I think this will make the most sense if we use a concrete example again. Know that, that this choice of big N is actually what we're looking for and what we would hope to choose. But here's what it would look like in a specific example. Say somebody wanted us to be within an error bound of, let's say 1/10 again. Then I would choose big N to be bigger than 1 over 1/10. And 1 over 1/10 is 10. So if I chose n to be, say, 11, then going out to the 11th term would make sure that I'm within 1/10 of epsilon. So this relationship, again, right here, gives us a relationship between n and epsilon that we need in order to say that this would converge for any epsilon, any small error bound that we'd want to go with. But yeah, that is pretty difficult, and I'm not going to make you guys do that on your own, especially when we're doing an online course. So let's keep going. We're going to look at some theorems that should make our lives a little bit easier when thinking about the limits of sequences. So the first one here, let's read it real quick. Suppose that f is a function defined for all x greater than or equal to x0, and suppose that a sub n is f of n for all natural numbers n greater than or equal to x0. Then the limit as x approaches infinity of f of x equals L implies that the limit as n approaches infinity of a sub n also equals L. What this means is that if you have a function that's based on the real numbers, in this case, f is our function that's based on the real numbers. We've got f of x going on here. If that function based on the real numbers approaches a limiting value L, and your sequence is enough like that function for all natural numbers n greater than some x0. So this basically says that for all x greater than some x0, that x0 is kind of like the first spot where the function and the sequence agree completely. But yeah, essentially, if we've got a function and a sequence that are agreeing completely as n goes on, then their limiting values are going to be the same. And so, yeah, if you're working with the same function where one is defined on the real numbers and the other is defined on the natural numbers, their limiting values as you approach infinity will be the same. And actually, if you were defining a sub n as f of n for all of the natural numbers, and not just for some number past x sub 0, a sub n would be called the restriction of f. So basically, a sub n is a function defined on the natural numbers, whereas f is its big brother that is defined on the real numbers. And they should have the same limiting values if they're so much alike. That's basically what that's saying. Moving on to the limit laws. Here we have just a bunch of limit laws. It's really important to recognize that these limit laws only work when an and bn are two sequences that have limits that actually exist, and they are both convergent sequences. It'll be very tempting later on to try to use these limit laws even when the individual sequences do not converge. But yeah, these limit laws behave the way that you would expect them to, just like normal operations, addition, subtraction, multiplication, division, all that stuff. Yeah, they're not super important. They work out the way that you would expect. The squeeze theorem is making a comeback here. And maybe I could do a little drawing for this one. Let's see. The squeeze theorem. We've got three sequences, an, bn, and cn. And we're going to make bn blue. bn is the sequence that kind of behaves erratically, but over time seems like it might be approaching a limiting value L. So I don't know, maybe L's out here. And it kind of looks like, BN settling down over time, getting closer and closer to this limiting value L. If we can sandwich this poorly behaved sequence with a couple nicely behaved sequences, so let's say AN's in the orange and it's a nice upper bound. That one's kind of horrible, sorry. And then CN could be down here. Oh, geez. All right, it's making dashes instead of dots. If you can find a sequence that always bounds the bad behaved sequence on the top and another sequence that always bounds the badly behaved sequence on the bottom, then you can squeeze the badly behaved sequence, and if both AN and CN converge to the same value L, then the middle sequence also converges to L. That's the squeeze theorem. Moving on to this next theorem, we've got the continuous function theorem for sequences. Let's just read this real quick. Let a sub n be a sequence with the limit as n goes to infinity of a sub n equals L. If f is a function that is continuous at L and defined for all a sub n, then the limit as n goes to infinity of the function f evaluated at a sub n is equal to f of L. Oh, this one's weird. We have a sequence, like an infinite sequence of numbers that we're kind of imagining going in here to the function f. a sub n is just the nth term in the sequence. And we're looking at how this limit behaves as n goes to infinity. This is weird because the term value is something that, when I'm plotting it up here, I'm plotting the term values kind of as y values, and the n values are kind of like our x values. And so what's weird here is that we're plugging in this sequence term, which is something we normally visualize as kind of a y value, but we're plugging it in to this function as in the place of like where an x value normally would be. So this is a weird object. If I had to settle down and try to summarize what's actually going on here, is that continuous functions, so f here is a continuous function, continuous functions don't mess up the convergence of converging sequences. So a sub n we know is convergent, f we know is continuous, and what we see here is that even though the function is plugged inside, even though the sequence is plugged inside of the function, the continuous function f doesn't mess up the convergence of converging sequences. This is going to be more clear probably even if we look at example 6, because part A, we're going to have to use this theorem a little bit. So part A here, we have the sequence where we've got 5 to the 1 over n. And that's going from n equals 1 to infinity. Essentially what we have here is a continuous function, 5 to the x, and inside of that continuous function is a sequence, 1 over n. And we're able to find the limit of these just thinking through the implications here. What's nice though is that since this is a continuous function for basically x equals 0, this is going to work out. If we look at what the sequence does as n goes to infinity, we get something that looks a lot like 1 over infinity, or this thing approaches 0, right, as n approaches infinity, which means that this overall sequence approaches 5 to the 0, which means that we approach 1 in the end. So yeah, that was actually an instance where we technically used this theorem, the continuous function theorem, for sequences. But that kind of makes it seem harder than it actually is. For the next one, finding the limit here, we've got a rational function, and the numerator and denominator of this rational function are both polynomials of degree 3. And so just like what we've done with limits in the past, we could technically use L'Hopital's rule here. Eventually though, like you expect, we're going to see that this limiting value ends up being 3 over 7, just the coefficients on those highest degree terms. And L'Hopital's rule is probably just the easiest way to say that happens. The last one, part C, it's weird, and honestly this is getting really long. I want to go through this quickly, so I'm going to cheat and move down towards what the book has. This is an instance where L'Hopital's rule is very necessary, where you end up doing some weird stuff with E and ln to make sure that you can get this weird function into a correct indeterminate form so that you can use L'Hopital's rule, and then you convert back in the end. And so yeah, you find out that this one equals 1 as well. The limit of this function, or the limit of this sequence, actually equals 1 as well. The last major two topics here are monotonicity and boundedness, which are two properties of sequences that allow us to determine the convergence of sequences in much simpler terms if they fit our criteria. So the first one's monotonicity, and a monotonic sequence is one that only increases or only decreases for all terms in the sequence. Real quickly, we could take a look at example 7. Here we have our nice n over n plus 1 sequence, and we could prove that the sequence is strictly increasing by looking at the nth and nth plus 1 terms. So, here they are. And if we go over here and make common denominators, and then think about how these numerators are related to each other, we can, prove that this guy is always greater than the other term. So the n plus 1th term is always bigger than the nth term, and therefore that sequence is strictly increasing. In part B, it's more boring. We've got b sub n equals n squared plus 6n. That's also definitely a strictly increasing sequence. We're just adding positive things together. The big question is, which of these two increasing sequences would converge? And I hope that if you think about it, you would recognize that the sequence in part A is going to converge, but the sequence in part B will not. The sequence in part A, actually, it's increasing all the time, but it's increasing at a slower and slower rate as n goes on. Whereas part B, it's increasing all the time, but it actually increases its rate of increase over time, and so it's just going to diverge towards infinity. But part A has some hope, because while it's still increasing, it's slowing down. And that's important. That brings us to our final major definition for the day, which is boundedness. And boundedness just means that you are restricting all of the terms in your sequence by some big number. And this first part, the big number is m. That's an upper bound for all the terms in the sequence. Similarly, you could say that it's below. We use little m for getting a lower bound. If it's bounded above and below, then it's a bounded sequence. That's just vocabulary. And then greatest lower bound, greatest lower bound and least upper bound are terms that we would focus more on in like a real analysis class, honestly. But yeah, just basically saying if there's some number where all of these sequence terms are less than this number, we're going to be bounded. That brings us to the monotonic sequence theorem, the bounded monotonic sequence theorem, which says that if you have an increasing sequence that's increasing monotonically, and it's bounded above, that necessarily means that the entire sequence is going to converge. Similarly, if you have a decreasing sequence that is bounded below, that sequence will converge. These two properties together give us some important criteria to say whether or not a sequence will converge, even if we don't exactly know what value the sequence will converge to. As long as we can be confident that we have an upper bound for an increasing sequence, or as long as we can be confident that we have a lower bound for a decreasing sequence, we can confidently say that we converge. All right, time for example 8. Example 8 is our last example for the lesson. And honestly, I want to make this quick too. In order to prove that this sequence a sub n, which starts off at, a sub 1 equals the square root of 2, a sub 2, if we're, using the second part of this, would be 2 plus a sub 1, which means that we've got the square root of 2 plus the square root of 2 underneath the square root. Yeah, a3 looks just as bad, if not worse. That would be the square root of 2 plus a sub 2, which means that we've got the square root of 2 plus the square root of 2 plus the square root of 2, all nested inside each other. The terms in this sequence look weird, and we have a recursive definition here that only tells us about, the next term based on the previous one. To use the bounded monotonic sequence theorem, we would need to prove that this thing is increasing. It looks like it's increasing, right? Because we're starting off at square root of 2. This looks like it's going to be bigger than the square root of 2. This looks like it's going to be even bigger than the preceding term. Because all of those square roots of 2 are still positive numbers. And so while we would do this formally using a method called induction, I think for right now, just looking, say, at these first 3 terms is enough to convince me that we're increasing and that we would kind of continue to increase. This is what it looks like in terms of induction. This is what we would do in a more formal math class, something upper level. And then that says that we're increasing. And we would also, if we're increasing, we would need to be bounded above. In order to prove that this thing is bounded above, we could probably take a look at the first 10 terms of this sequence and see that it's approaching the value 2 and take that as a guess and try to make it, an upper bound. I'm just going to skip down to here. Again, formally, we would be using induction to prove that the sequence is bounded above by the number 2. It starts off with a base step, so you're asking yourself the question, is the first term less than 2? Is the first term less than 2? Yes, the first term is less than 2 because it's the square root of 2. And then this next case is called an inductive step, this next step is called an inductive step, where you assume the thing that you're kind of trying to prove, you assume that each term in the sequence is less than 2, and then you look at the next term in the sequence, a sub n plus 1. And using that, you can prove that the next term is less than 2, and that essentially proves that the sequence is bounded above by 2. So in this way, we've shown that this sequence is increasing and bounded above, so we could definitely say the sequence converges even if we're not completely sure that the limiting value is 2. All right, I think we're going to wrap things up here. This has been How to Math with Dr. Ian Lundholm. Remember, you have online homework to do, and now you're ready for it. I'll see you in the next one.